All right, so our next question is, what is the electric potential 1 centimeter away from a 1 nanocoulomb charge? And then as a follow-up, what's the potential difference between an initial point 1 centimeter away and a final point 3 centimeters away? So what we are looking at is we have, I'll draw this as a plus. So this is a 1 nanocoulomb charge. And we are trying to figure out the potential 1 centimeter away. So now this distance here is 1 centimeter. And then also another point that would be 3 centimeters away. So I'll try to kind of draw a distance at 3 times that distance. 1, 2, 3. And draw it as being here. So that distance there is 3 centimeters. So a couple of things to pick up on the wording of this question is it seems like you're asking for 2 different things, but we're not. Right? Electric potential and voltage, those are 3 words that mean the same thing. The only thing that is thrown in here is this word difference in the end, because in the second half of this question, we're actually looking for, we'll want to calculate the potential here and the potential here and then subtract them. So we'll be looking at the potential difference, the change in voltage between a final spot here and an initial spot here. So in this one, we're looking for V, and in this one, we're looking for delta V, which is going to be the delta V, which is V at 3 centimeters minus V at 5 centimeters. That delta triangle always and has always meant the final minus the initial. So the wording of this problem says the initial is 1 and the final is 3, so it'll be 3 minus 1 centimeter. And we kind of already know a few things about what this is going to look like. So this is basically a single positive charge, and that would be, if you want to draw the analogy with the sheet, that would be kind of a sheet that has a positive charge here, and it would look something like that. And we'd know that the electric field lines point down the hill, and the potential lines of constant potential would go something like that, just around in the circle. And so the equation that we're going to use here is that V is KQ over R. That's Q. These are our 2 R's. And K is a constant. It's 8.99 times 10 to the 9th. And the units on that are, oops, of course I didn't write them down. Newton meter squared per coulomb squared. All right, so our V at 1 centimeter, so V, the potential at this location, which is 1 centimeter away from the charge. I could have just as easily drawn it here, right? That distance there is 1 centimeter too. Or really anything that was a whole circle 1 centimeter away, is going to be 8.99 times 10 to the 9th Newton meter squared per coulomb squared times Q, which is, I guess that, so 1.0 times 10 to the negative 9th coulombs. Make sure you get them into metric units here. And then we'll divide by R, and R needs to be in metric as well, so 1 centimeter away is 0.01 meters. And if you plug that into your calculator, you will find that V1 is 900 newtons per coulomb. And we want to write this as a 2 sig fig answer, so that would be 9.0 times 10 to the 2nd Newton per coulomb. So that's the answer to the first question, the first part of this. It's 900 newtons per coulomb. And now we're looking for the potential difference between 1 centimeter and 3 centimeters. So for that, we already have the 1 centimeter answer. We need to calculate the 3 centimeter answer. So we use the same methods. It needs some more space. I'll erase that. So V of 3 centimeters is going to be K, which is that same number, I won't rewrite it, times the same Q, 1.0 times 10 to the negative 9th coulombs, divided by now 3 centimeters away. And that better be a third as much, so that should be 300 newtons per coulomb. So that is and the delta V is going to be that number minus that number, so that's going to be the 3 centimeter answer, 300 newtons per coulomb, minus 900. And that is negative 600. And I'll go ahead and write that as a volt. 1 volt is 1 newton per coulomb, so either of those units would be just fine. So that is the definition of a volt, is that 1 volt is 1 newton per coulomb. The negative here is important because we're going final minus initial, but otherwise that's how that would work. So next up is everyone's favorite Newton's third law question. Coulomb's law is anytime you have these two things, they're action-reaction pairs. So these are two positive charges, so they will repel each other. And so I know that it has to point in that direction. And you cannot push, even though this has twice as much charge as that one, they push equally on each other. That is Newton's third law. So the answer to this is B. And the number 9 is proton released from rest at this spot here. And afterward, what does the proton do? And we've been given potential here, or voltage. So we know that high potential is here, low potential is here. The 0 volts is kind of meaningless. It doesn't mean that it's not going to move at 0 volts, right? That's what we do know is that the electric field points down the hill. So our electric field lines point like that. That's what E looks like. So they're perpendicular to the lines of constant potential. We call those lines equal potential surfaces. And basically this is, if you want to imagine the sheet, this is like the sheet that is just kind of tilted up like that. I don't know if that's something that visually works with the video camera. But if we place, so we have the top of the hill here and the bottom of the hill here, it's just sort of a straight flat sheet. So we put a proton here. Protons always go in the direction of electric field lines because they're positive charges. So proton here will just roll straight down the hill. As it rolls down the hill, it'll speed up. It'll gain kinetic energy. It'll lose potential energy. So the answer there is E. It should move downward and it should speed up as it does.